So here's section 2.7 where we're going to work on actually applying some of that constant acceleration type problems. Here we're going to try to understand what types of problems can be modeled as a free fall problem and be able to actually solve those types of problems using our kinematic equations. So let's say that you drop two objects, one heavy one, one light one. Which one's going to hit the ground first? Well, the answer is that without air resistance, they would both actually hit the ground at the exact same time. Each one has the same acceleration, the acceleration due to gravity, and each one has the same initial velocity of 0 since you dropped them from rest. So the question is, why do feathers and coins, for example, have different times of fall? When air resistance is present, it basically acts as a type of friction, a friction that's going to affect different objects differently, which means that the feather is going to have more drag on it, and that's going to lower the terminal velocity of the feather and allow the coin to fall first. But when we ignore air resistance, or when air resistance is negligible, that's when we have what we call a free fall problem. Free fall is when air resistance is ignored and your acceleration is that acceleration due to gravity, which is about 9.8 meters per second squared anytime you're near the surface of Earth. Now this particular model works for lots of different types of problems. It's actually a great approximation that we can use, and it simplifies problems a little bit. So free fall problems don't have to have the object drop from rest. In fact, the only stipulation is that they have to be solely under the influence of gravity. So they could be thrown upward, thrown downward, thrown sideways, different things like that. So we'll see some different examples as we work through this section. Free fall is really just another form of a constant acceleration problem. The only difference is that we're going to use the y subscript instead of the x because the thing is going to be moving in an up and down direction rather than left and right. Let's start off by understanding what the different acceleration and velocity vectors look like when you're talking about a free fall problem. So let's assume that you have maybe a ball that you throw up in the air. And we're going to throw this ball straight up in the air so that it's going to go straight up and come right back down. I'm going to kind of spread the drawings out so that I have some room to draw some vectors on these objects. But let's assume that the ball is going straight up and straight down. What that means is that when I draw the velocity vectors on this ball, the velocity vectors are ones that are going to be going straight up on the way up and straight down on the way down, where this would now be the initial velocity of the ball. As it continues to rise, that velocity is going to get a little bit smaller and smaller until at the very peak of its path, the velocity is going to have to hit a 0 velocity. This is going to be important. It's going to help us understand how to solve some problems when we actually start using our kinematic equations. Knowing that when you get to the peak of your path, your velocity at that point is going to be 0, because the peak of the path is where the object is going to change directions. And anything when it changes directions is going to have to hit that 0 velocity before it turns around and starts going the other direction. Now as it begins to fall again, the velocity is going to be a little bit smaller when it first begins to fall, but that velocity is going to be speeding up and get faster and faster until you get to that final velocity at the end. So these arrows are going to be the longer arrows here, and you have shorter arrows when you're closer to the peak of the path. Now if I pull out a different color here and draw in the acceleration vectors at each point are going to be an acceleration caused by gravity. We know that near the surface of Earth, that acceleration due to gravity is negative 9.8 meters per second squared. Negative because acceleration due to gravity is always pulling the object downward towards the center of the Earth. So you'll notice that as I draw these acceleration vectors, everywhere I draw them, I'm drawing them pointing downwards. Because again, gravity never pulls things up, it always pulls things downwards. So even though velocity is going with the flight of the ball, both up and down, you're going to find that acceleration always downward. When acceleration is working against the direction of the velocity, we see that that object is slowing down and getting slower and slower until it hits that 0 velocity. On the other hand, when we look at where the acceleration and the velocity vectors are pointing the same way, we see that that object is speeding up until we get to this final velocity where it's moving fastest. Now let's look at an example where we can start to apply some of our kinematic equations to actually solve some problems dealing with free fall. So let's say that you have a stone that's thrown upward from the top of a 50-meter high building. Here's our building. Here's the ground down here. This building's going to be 50 meters tall. And here's maybe some little guy that's standing at the top of this. He has this ball, throws it straight up in the air. It's going to go up, it's going to come back down, and eventually come down to the ground. This stone is going to be thrown in the upward direction at 20 meters per second initially. And we're going to start by determining the time at which the stone will reach its maximum height. Now again, talking about maximum height is an interesting point along the path to look at. And like we said on the last slide, it's important to note that we know that the velocity at this point is going to be 0 meters per second. That's going to help us in solving for this. So determining the time at which it reaches that point, we can go to our equation for final velocity, knowing that the final velocity at that particular point at the peak is going to be 0. And now when I go to my equation, VF equals VI plus AT, I know that my final velocity is going to be 0. My initial velocity was 20. And the acceleration in a free fall problem is always that negative 9.8 meters per second squared anytime I'm near the surface of Earth. So if you go ahead and pause the video, plug this into your calculator and solve for it, you can find out what that time is where you reach the peak. If you've done that, you'd find that it reaches the peak at about 2.04 seconds. Another interesting thing to look at would be what that maximum height actually is. So we can use more of our kinematic equations to figure out how high is the ball at that particular point, or is the stone. An equation that we could use here is we could use the change in position being the initial velocity multiplied by the time plus a 1/2 AT squared. If we call the top of the building our initial position, or maybe call that the origin, we could just find the height that the stone will reach above that position where our initial velocity is still those 20 meters per second. The time now for it to reach the peak we now know is 2.04 seconds. Half of negative 9.8 is negative 4.9, and I can square the time to find out what is this change in position going to be from the rooftop. Again, go ahead, plug that into your calculators, and you'd find that that change in position is about 20.4 meters. So we know that this object is going to reach 20.4 meters above the rooftop, which if we wanted to report that as a total height above ground, we could add it to the 50 and get 70.4 meters above ground. Let's look at a couple more questions that you could look at related to, again, this free fall problem. In this case, there's other things that we might look at that are interesting to solve for. For example, these questions are asking you to determine the time at which the stone actually returns to the level of the thrower. So again, the stone was thrown from the top of the building. It went up in the air, and eventually it's going to come back down and pass the thrower again on its way back down. And this question is looking at when is it going to get there and how fast is it going once it does reach that particular position. So if we want to find the time that it reaches that spot, we can use that same kinematic equation that we were just using in looking at change in position being equal to a VIT plus a 1/2 AT squared. In this case, our change in position is going to be 0 meters. Because the ball started at the height of the building, it went up, it came back down, and we're talking about it being at that exact same position. So in terms of its height above ground, it has not changed its height above ground at all. The initial velocity is still 20. We want to find out when it gets there, and again, half of negative 9.8 is a negative 4.9 t squared. Now when you solve for this, you can pull a t out, and you're left with the 20 minus 4.9 t. So that when you solve for this time, you can have your t equal to 0, or you could also take the 20 minus 4.9 t and set that equal to 0. So what you're noticing is that you actually get two different solutions to this problem. Either you get t equals 0, or when you solve this, you get t equal to about 4.08 seconds. Now that makes sense to have two different times because really what you're solving for are the two times when the ball is in that position of being at the rooftop. And it is there at the beginning of the problem at t equals 0, and it's also there again 4.08 seconds later. Now to find out how fast it's moving when it's at that position, go back to that equation for final velocity being the initial velocity plus at, and that velocity is going to be equal to our starting velocity of 20 minus our acceleration of 9.8 multiplied by the time of 4.08 seconds. When you solve for this, it's interesting to see that that final velocity is negative 20 meters per second, which again is a value that makes a lot of sense. Because if we ignore air resistance, as fast as you throw the ball up in the beginning, it's going to come down and it will hit the exact same speed on its way down as what you threw it up in the air with. Because again, you have this symmetric path that's there. So it should be moving with the same exact speed, but only this time in the opposite direction as it's coming back down the side of the building. Let's look at two more questions that are interesting to look at and answer. These questions ask about the position and the velocity of the object at a certain point in time. And what you'll find here is that the same couple of equations that we've been using can be used for these couple of questions as well. For the first one, we can look at the position of the object at the 5-second point in time. So at 5 seconds into the motion, if we want to know where the object is, again, put in your initial velocity, put in the time of 5 seconds, half of negative 9.8 is negative 4.9, and again, my time that I'm using is 5. So if I actually put all of this in and I solve for where this object is after 5 seconds into the motion, I'll let you guys plug it into your calculators and solve for that. And you'd find that after 5 seconds into the motion, you get about 22.5 meters in the negative direction, which basically means if we were calling the top of the building the origin and the 0 point, then this ball has already passed the top of the building and is now about halfway down the building. And that's what we mean by a negative 22.5 meters. If I wanted to find out how fast it was going at that point, I can again use the VF equals VI plus AT, and I could find that my velocity at that point in time, when I plug all of this in, would come out to be about negative 29 meters per second. Again, the negative indicates that it's moving in the downward direction towards the earth. The last thing that I want to show you is what about at 6 seconds into the motion? Where is this object then? Again, if you use this same equation that we were using here and plug in 6 seconds worth of time instead, there is something interesting that you'll notice. When you plug that in and solve for delta y, you find that you get a change in position of negative 56.4 meters. Now again, the building was only 50 meters high, so if we were at negative 56, it means that we've passed the top of the building, gone downwards, and we're actually, if this is the ground, we're actually more than 6 meters below the ground at that point. Now obviously this thing isn't going to burrow its way into the ground that far. What we're finding here is that we do need to be cognizant of what the setup of this problem actually is. And although the math is telling us that it's at a negative 56.4 meters, realistically by this time, after 6 seconds into the motion, the ball has now hit the ground, impacted the ground, and is probably just sitting there at rest by this time. So the ball didn't take that long to actually go up in there and come back down. Really, total time in the air would have been something more than 5 seconds, but less than 6. And we could also have solved for the impact velocity of how fast it was going when it hit the ground. We'll try some problems like that when we come back to class. But hopefully this gave you a little bit of an introduction as to how to set up free fall problems and how to utilize those kinematic equations to solve for various interesting points that might be along that motion.